Thus far, when we've looked at confidence intervals, we've assumed that our data follows a Gaussian distribution. And it turns out that for small sample sizes, this isn't a very reliable approximation. So, in order to come up with better results, a chemist who went by the pen name of Student introduced a new distribution, and it was called Student's T distribution. So now, whenever we figure out our confidence interval, delta, instead of using eta, the variable from the standard normal deviation, we'll use t from the t distribution. And here are some differences between those two methods. We're going to use a table, but they look a lot different because instead of there just being one curve as for the standard normal distribution, for the t distribution there are several curves, and they, depending on the number nu, which is degrees of freedom. So here in the horizontal area, that is this area here, we have values for t instead of the area. For the standard normal integral table, we get the areas are from 0 to eta, but for the t table, it's the area from negative t to t. And those areas are the columns. So here we have 50 or 0.5, 0.8, 0.9, 0.95, etc. So we have common values for the probabilities that we want instead of all these values. Now, like I said, we have values for t here in the area. So if we wanted to find t for 80% probability, we would just find the intersect between the t80 column and the number of degrees of freedom in our system. For example, if we want to find the confidence interval, the 90% confidence interval for this system, we'll look at that both with the student's t distribution and the standard normal distribution. Since we're familiar already with confidence interval using standard normal, let's go to the t distribution. Now we want to find the t value that corresponds to an area of 0.9 and nu value of 9. So first let's find the t90 column, and then the value that corresponds to nu equals 9. So we get t is 1.833 for a 90% confidence interval for the system. And then to find eta, we will look for the area that's 0.9 over 2, so that's between these two values. And we get that eta is between 1.64 and 1.65, so we get 1.645 after linear interpolation. Now, let's see the effect of these different values. Our delta, if we're using the standard normal distribution, is 3.12, and if we're using student's t distribution, we have 3.48. So for small sample sizes, eta underestimates the uncertainty. As you know, for a population with a mean, if we take two samples from that population, the sample means will probably not be equal, and they probably won't equal the the population mean. So we can use the t distribution to perform a t-test to see if the two samples are likely to come from the same population. Now, we start with the confidence interval, but we let delta equal the difference between the two means, like you can see here. So the process is to calculate t based on that delta and then compare it to the t that we would expect for that confidence level. So here is the actual t that we get for these two samples, comparing these two samples. And now we want to see what the t should be for this confidence interval. Here again is the t table, and the area represents the confidence level, and this unshaded area would be the significance level. So the t that we would expect to find for our confidence is found by taking the significance level and then dividing that by 2 and getting the corresponding value of t. So for example, we're looking for, say, an 80% confidence level. Then that gives us a significance level of 20. We divide that by 2, and that would tell us that we want to find the t90 value. If the actual t that we found is smaller than the expected t, then we can say that these two samples are likely from the same population. And one note, we want this to be positive, this delta to be positive, so set the larger of the two means to be xm1. Now in general, the two samples don't have the same standard deviation and the number, or the sample size. So we want to figure out some sort of average value or some value to use for sample standard deviation and n. So here we'll compute t based on this, and nu is also computed using the sample standard deviation and n for the two samples. But the test is performed the same once we have this value of t and nu, the same as if we had samples with the same s and n. Here's an example. We have these two samples and we want to see if they come from the same population. Specifically, we sampled people from Kansas to see how much they spend on movies per month, and we sampled people from New York to see how much they spend on movies per month. And we want to see if really it's likely that people in Kansas and New York spend the same amount on movies per month. So even though our sample means are different, we want to see if they come from the same population. So if people in Kansas and New York are the same population, that is, they, in this context, they spend the same amount on movies per month. Now, if we were able to ask everybody in Kansas and everybody in New York, then we would be able to know this definitively. But since we just have sample sizes of 5 and 10, we'll use a t-test to predict whether or not they come from the same population, or if there really is a difference between the average amount spent by people in Kansas and New York. Okay, we'll start by computing the actual value of t, so the differences between our sample means and then this value for sample standard deviation. We come up with 2.5. Nu is computed like this according to standard deviation and n, and we come up with 7.51. Now this value is always rounded down for the t-test, so 7 is our value for nu. And we want to be able to say with 80% confidence whether or not people in Kansas and people in New York spend the same amount on movies. So our confidence level is 80%, that means our significance level is 20%, and to find t, we want to divide that by 2, and that'll give us our value for t. So we have t90. And on the t90 column, the row for nu equals 7 gives us 1.895, which is less than 2.5, the actual value for t that we computed. So we cannot say with 80% confidence that New Yorkers and Kansans spend the same amount on movies per month. In other words, we're 80% confident that people in Kansas do spend a different amount of money than people in New York every month on movies.